If p of x is a polynomial in x and if k is any real number, then the value obtained by replacing x by k in p of x is called the value of p of x at x equals k and is denoted by p of k. Also, if p of k equal to 0, then k is called as the 0 of the polynomial p of x. The number of zeros in a polynomial in one variable is based on its degree. So, a linear polynomial has one and only one zero, a quadratic polynomial has two zeros, and a cubic polynomial has three zeros. For a linear polynomial, p of x equals ax plus b, where a not equal to 0, if a real number k is the 0, then p of k equal to 0, that is ak plus b equal to 0, which implies that k equals minus b by a. So, minus b by a is the 0 of a linear polynomial ax plus b and is actually minus constant term divided by coefficient of x. Thus, the 0 of a linear polynomial is related to its coefficients. But what about the zeros of quadratic and cubic polynomials? Let's find out. For a quadratic polynomial, to get the zeros, at first we need to factorize by splitting the middle term. For example, the polynomial p of x equals 2x square minus 8x plus 6 can be factorized to 2 into x minus 1 into x minus 3. To get the zeros, put p of x equal to 0, then we get x equal to 1 or x equal to 3. Therefore, the zeros of the polynomial 2x square minus 8x plus 6 are 1 and 3. Comparing them with the coefficients of the polynomial, we get sum of the zeros equals 1 plus 3, which is equal to 4, which can be written as minus of minus 8 by 2, and that is equal to minus of coefficient of x divided by coefficient of x square, and the product of the zeros equals 1 into 3 equals 3, which can be written as 6 by 2, which is equal to constant term divided by coefficient of x square. Let's confirm this by considering alpha and beta as the zeros of the polynomial p of x equals ax square plus bx plus c, where a not equal to 0. Then surely x minus alpha and x minus beta will be the factors of p of x. Therefore, for a constant k, ax square plus bx plus c equals k into x minus alpha into x minus beta. Multiplying throughout, we get kx square minus k into alpha plus beta into x plus k alpha beta. Now comparing the coefficients of x square, x and constant terms on both sides, we get a equals k, b equals minus k into alpha plus beta, and c equals k alpha beta. So, we can come to a conclusion that alpha plus beta equals minus b by a and alpha into beta equals c by a. Or we can say that sum of zeros equals minus of coefficient of x divided by coefficient of x square, and product of zeros equals constant term divided by coefficient of x square. Now let's use this in a problem. Find the zeros of the quadratic polynomial 6x square plus 17x plus 5 and verify the relationship between the zeros and the coefficients. Given p of x equals 6x square plus 17x plus 5. Upon factorization, we get it as 3x plus 1 into 2x plus 5. To get the zeros, we put p of x equal to 0. So 3x plus 1 equal to 0 or 2x plus 5 equal to 0, which implies that x equals minus 1 by 3 or x equals minus 5 by 2. Therefore, the zeros of the polynomial 6x square plus 17x plus 5 are minus 1 by 3 and minus 5 by 2. Now, let's verify the relationship between the zeros and the coefficients. Sum of the zeros equals minus 1 by 3 plus minus 5 by 2, which is equal to minus 17 by 6, which is minus of coefficient of x divided by coefficient of x square. Now, product of zeros equals minus 1 by 3 into minus 5 by 2, which is 5 by 6, and that is constant term divided by coefficient of x square, hence verified. So that's the relation for quadratic polynomials. Now what about the zeros and coefficients of a cubic polynomial? Let's find out. For a cubic polynomial, to get the zeros at first, we need to factorize by trial or long division method and then splitting the middle term. Consider a cubic polynomial p of x equals 2x cube minus 5x square minus 14x plus 8. We get the zeros when p of x equal to 0 as x equal to 4, minus 2 and 1 by 2. Comparing the zeros and coefficients of the polynomials, we get sum of the zeros equals 4 plus minus 2 plus 1 by 2 equals 5 by 2, which can be written as minus of minus 5 by 2, which is equal to minus of coefficient of x square divided by coefficient of x cube. Product of zeros equals 4 into minus 2 into 1 by 2, which is equal to minus 4, which can be written as minus 8 by 2, which is equal to minus constant term divided by coefficient of x cube. And the sum of the products of the zeros taken 2 at a time, that is 4 into minus 2 plus minus 2 into 1 by 2 plus 1 by 2 into 4 is equal to minus 7 and can be written as minus 14 by 2, which is equal to coefficient of x divided by coefficient of x cube. We can confirm this by considering that if alpha, beta and gamma as the zeros of the polynomial p of x equals ax cube plus bx square plus cx plus d where a not equal to 0, then alpha plus beta plus gamma equals minus b by a. Alpha beta plus beta gamma plus gamma alpha equals c by a, and alpha beta gamma equals minus d by a. Or we can say that sum of the zeros equals minus coefficient of x square divided by coefficient of x cube. Sum of product of the zeros taken 2 at a time equals coefficient of x divided by coefficient of x cube, and product of the zeros equals minus constant term divided by coefficient of x cube. So we can conclude that there is some relationship between the zeros and the coefficients of a polynomial in one variable. For a linear polynomial, the one and only one zero will be equal to minus constant term divided by coefficient of x. For a quadratic polynomial, the sum of the two zeros will be equal to minus coefficient of x divided by coefficient of x square, and the product of the two zeros will be constant term divided by coefficient of x square. And for a cubic polynomial, the sum of the three zeros will be equal to minus coefficient of x square divided by coefficient of x cube. The sum of the products of the three zeros taken 2 at a time will be coefficient of x divided by coefficient of x cube, and the product of the three zeros will be equal to minus constant term divided by coefficient of x cube.